So I think where we were was the following, that we said this Ix prime, Iy prime, they're basically rotated, right? So what we got finally was Ix prime equals Ix cosine phi plus Iy sine phi. Likewise, Iy prime is minus Ix sine phi plus Iy cosine phi, and the Iz has, because you're going around the z axis. So this was one result we got, and then we also wrote down that we can write down I plus I minus, right? Ix plus Iy and so on. And so Ix prime plus Iy prime. So this sort of raising operator in this rotated situation is I plus e to the minus I phi, and likewise with the minus sign here. So the I minus in the rotated one will have a minus sign here and a plus. Right, so I think this is where we ended last time. Okay, so remember what we want to do now. So just again recalling, in the classical picture we could get that what the dynamics of the moment is, that you rotate by pi over 2, etc. And the RF is on, then you keep precessing about this at resonance about the x prime axis, the moment keeps precessing. So it will go from pointing along z direction to minus z plus z minus z, continuously that will keep happening. We want to look at it now from this quantum mechanical picture. So we want to write down I h bar d psi dt equals Hamiltonian psi, and then time development. Based on that, we want expectation value of mu z. So that's where we are headed, right? So this is useful because once identified these, we can rewrite. So once again, I have this H is the magnetic field. Okay, the curly H is the Hamiltonian. This is now I h1 cos omega zt plus j h1 sin omega zt, and then you have of course the DC field, right? So you have a Z field, and then you have the RF field in the XY plane. Okay, and then you have I h bar del psi del t is Hamiltonian acting on the wave function, and then Hamiltonian is of course minus mu dot h. Okay, so and mu again in terms of the angular momentum and so on, gamma h bar, so on. So you can write this as so minus gamma h bar, and then you have h naught I z, right? So you have a z component of the moment operator that will have a I z, and the dot product with the field with this one, it gives a h naught I z, and then the other one you'll get h1, and then you have a Ix cos omega zt plus IY sine omega acting on wave function. Right? So with the x component of moment, that goes with h1, so cos omega t, so that's this one. Y component of moment, which contains IY, that goes with this one here, so h1 sine omega t, so that's this. Now, so what is this quantity? Right, so this quantity, right? Not yet. I mean, this is just so Ix cos omega plus Iy sin omega.
Ix prime.
Ix prime, right? So that operator there is Ix prime. Okay, so right. So this is Ix prime. So Ix bar. Ix bar del psi del t equals minus gamma h bar h naught Iz and plus h1 Ix prime acting on the wave function. Okay, so you remember what we want to do now? Yeah, a little bit later, but we want to. So there was a time dependence in the Hamiltonian. It's sort of gone now in some way, because if you define with respect to different axis, it's gone. So the time dependence will be now in the wave function. We'll write the following way. So we define psi prime as basically the rotated in some sense e to the I omega z I z t. Sorry. Okay, we define it like this. So our equation is in terms of the wave function. So we write now psi is e to the minus I omega z I z t psi prime. Okay. So if you now put this back in your Schrodinger equation, so here. So firstly the h bar anyway goes, and then you write the time derivative and so on. Right? So d psi dt you can write down, okay, and then something e psi prime dt. So if you from this you can write d psi dt as, so you take a derivative of this one, you will get a minus I omega z I z e to the minus I omega z I z t psi prime. This is one term, and then plus e to the minus I omega z I z t del psi. Okay, so if I now do IH bar on this side as well as IH bar on this side, okay, then I can replace my left hand side right? Here in the left hand side I have this I bar del psi del t. So writing psi in terms of psi prime, I can replace that here also and write psi in terms of psi prime. So I can get an equation only in psi prime, right? This is I bar del psi del t, it has something psi prime, something del psi prime del t. And likewise, if you just continue that, what you will, and then, so I just skip another step. If you, then you also multiply from the left by, see you have some e to the minus I omega z I z t. So you multiply from the left by e to the plus I omega z I z t. Okay, so what are we doing? We started with the Schrodinger equation. We defined a psi prime, which is basically time evolution in some sense, rotation with time, right? So when you have a I theta t operator, basically rotating the wave function, and then we rewrite the wave function in terms of psi prime, take derivative, and then put that back in the Schrodinger equation, and you notice you have a e to the minus I omega z I z t. So I multiply from the left by e to the plus I omega z I z t. So this will also appear over here, okay, and with
that factor actually can directly be taken from the left hand side also, right?
also, yeah,
Psi
yeah.
already has this.
Yes. Psi already has that. So if you now take this, so just fairly simple algebra, what you get is minus I omega z I z psi prime plus del psi prime del t equals I gamma h naught I z psi prime and plus h1 I x psi prime. Sorry?
It's prime.
Written ix everywhere. I think this is continues as ix because x ix prime, right?
Yes.
Yeah, we have ix prime here.
So substitute
Yeah.
psi prime.
So, and this right here, this should be ix prime. H1. Is that correct? I think I missed writing the. Yeah, that's the reason.
Why did we get ix? Because there is also the density transformation because of the experience.
Yeah. So I'm just. So we have. So ix constant dot t. H1 into Yeah. So actually, what happens is the following. You see, your so let me just write ix plus omega z t plus iy sin omega z t, which is of course ix prime, but also same as e to the minus I omega z I z t I x to the plus I omega z one side be a right side prime, right? So when I actually I'll write this as psi prime e to the this thing psi prime e to the minus and then multiply from the left by e to the plus, then I will get ix prime sandwiched between e to the minus and e to the plus. So that goes back to ix, right? We have ix prime here, and then I rewrite my wave function as, using this one. So I write this as then there is a e to the minus I omega z I z t times psi prime. Okay, then from the left I have to multiply by e to the plus I omega z I z t. No, it's from the left.
तो प्लस आई वो x प्राइम
So what I get is a term like
So IZ prime is equal to IZ. I think that's why we are getting the same term. So because
IZ prime is IZ, yes. Rotation is about the Z. So it goes the other way now, right? So you will have actually plus minus. Okay, so you go back to Ix over here. I verify once, but this seems okay. Right? Everybody with me? So, right, so we can basically write this. You can move this one on the other side. This is together with this one. You have a psi prime, so you have a x naught here, and then here you have some gamma I, okay, other than the psi prime. So gamma h naught, and on this side is minus. So I gamma h naught, and here it is minus I omega instead of this. So the same IZ, right? So you group these terms, and then again, if you want to write in the Schrodinger equation form, you will write IH bar del psi prime del t. So if you are uncomfortable with this, you can do a IH bar here, and also have another IH bar here. So whatever sign you get, so you will get a gamma h bar. And the I square gives -1, and then you together, so this will give you again +1, and so on. And so once you compact all that, what you get is IH bar del psi prime del t equals minus, both have the same sign, h bar omega z plus gamma h naught iz plus gamma h bar h1 ix acting on side line. Right, that looks okay. So just to check once again. So for this term, you will have a, from here you will have a I square, so minus 1, so minus gamma h bar h1 ix, so the minus is here, then gamma h bar h1 ix, so this is okay. Likewise, the other term, again with this I square you'll have a minus sign, and this one here also same way. I'll have a plus sign on this side. I square is minus 1, and then I have h bar etc. So I move that to the other side, again a minus sign, and so you'll get a h bar omega iz. Okay. So, h bar omega iz. Okay. So what has happened now? I have rewritten. So I do have a RF field present actually. The time dependence from these operator parts is gone. Okay, it's there in the psi prime now. Psi prime is some e to the something psi. Okay, so this now looks like just minus gamma h bar h effective, right?
We started off the other way, put the time dependence in the operators.
Yes.
And then
Yes, we had the time dependence in the operators, and then now we have removed that, and now it's gone into the wave function. Point is now, so this is the equivalent of the rotating frame coordinate transformation. That in classical picture, what do you do when you have to rewrite the equations of motion in a rotating frame? This is what it is now. We are rewriting in the rotating frame. There is no time dependence of the fields now. It's gone. No, there is no T. There is no explicit time dependence. The time dependence is there over here in some way. So this is like going to the rotating frame, and you describe. So now once we solve this, you can find expectation values, all that. Okay. So we have, you know, one-to-one match with the classical description. So if you now choose omega z as minus gamma h naught, so in the k direction, then this is gone. Okay, and the remaining is the RF, and so all the precession happens. You know, classical picture, the precession happens around the x prime direction.
the resonance condition.
At resonance condition, yeah. So resonance condition is when this is 0. Okay. So in the lab frame, the wave function is stationary, and Ix moves forward. In this rotating frame, it's the other way. Ix is stationary, and it's the way psi prime is the one that changes. Okay, it rotates backward. So you basically now have I h bar del psi prime del t equals h prime at p1 psi. Okay, and then what is the wave function? Right, so we've just called this one as the Hamiltonian as viewed in the like rotating frame, this effective field. So no time dependence in the Hamiltonian anymore. All the time dependence is in the wave function. So, from this, of course, psi prime, the usual picture is that e to the minus I by h bar h prime t, right? And psi prime is equal. That's the time evolution of the wave function. Okay. Then further you can write psi prime in terms of psi. Okay, we have defined that earlier. Okay, and so finally you'll get wave function evaluation is minus e to the minus I omega z I z t and then this one also e to the minus I by h bar h prime. This is the Hamiltonian h prime t and multiplying psi prime psi of this already was psi prime, so yeah. Okay, so you have done this, you know the wave function. See, our intention was what? We want to calculate expectation values. How does the mu z depend on time? Okay, now you have the time dependence of the wave function. So expectation values, you just have to do the integral, no? Psi star something psi. So you want to calculate, let's say, this quantity. So straightforward, right? So you just do integral psi star t mu z, whatever is that operator, psi t, and well integrated over whatever is the spin in the space. Right? So this is of course gamma h bar I z. You have the wave function, you can write the complex conjugate. You have the wave function here, so you can work this algebra. Just write a couple of steps. So if you actually do mu z t, from in the psi star you'll get e to the minus I omega z I z t and e to the plus I by so I h bar omega 1 I x. Remember Hamiltonian, we are considering resonance condition. So there is no h naught anymore, and so you have just the h1 part, h1 gamma h1, so omega 1 is gamma h1. Okay, so with that sort of nomenclature, you have I h bar omega 1 ix here, and then so this complex conjugate, right? So this is the wave function psi star, and then you have this gamma h bar iz, and then likewise you will put without the complex conjugate, just the psi. Then so this will write as e to the if psi 0 star. Okay, and then this can be then written as, we have said that before, psi star 0 e to the minus I. Okay, another thing, so what you have done is this e to the minus if you move to this side next to the iz now. But also another point is that, so it's like a e to the ib, which is e to the ib times a. A and B commute, then A e to the IB is e to the IB A. Okay, so what we are going to put together is, so from here you are going to have an e to the minus I omega z I z t from here. Right? You'll have one term e to the minus I omega z I z t. Right? So I z multiplying e to the minus I omega z I z t. So that's like this form. This is A, and this is this. Okay. I can, because this contains I z, this contains I z, they commute. I can interchange. Okay, so I can move the I z that side. Okay. So then what you will have is I z sandwiched between e to the plus I h bar omega 1 I x, and from that side e to the minus I h bar omega 1 I x.
This will be the minus psi star.
Oh, psi star, yeah, sorry, other way around. This will be having a minus sign, the other side is a plus sign. Yeah. Correct, yeah. So, yeah. So, this will then have a plus sign, psi star 0 into the minus I. So, this will also have a plus sign on this side. Yeah. Right? So, after you doing all this, one part you will get contains, so you get this mu z as gamma h bar psi star 0 e to the minus I. The other part, with e to the omega z, I z and all that, multiplying the complex conjugate, that will give you 1. What you have remaining is psi star 0 e to the I omega 1 t ix, iz and e to the plus I omega 1 t ix d tau. Right, am I? Yeah. So on the left hand side you'll have a negative sign in the exponent, and right hand side a positive one in the exponent. Okay, that's what this is. Okay, this is z, not x. Another psi 0 will be there, yes. Yeah. Okay, now just to remind you, what we found earlier is e to the minus iz phi ix e to the iz phi, right? So this is the rotated ix prime. So ix cosine phi plus iy sin phi. You can associate something here with the angle, right? This omega 1 t is basically the angle. Likewise, if you put iy here, then again rotation about the z-axis, so minus ix sin phi plus iy cosine phi, and with the z. So you can go, see here we want something a little different. Here we have iz over here and ix, so it's rotation about the x-axis actually. So but by cyclic permutation you can go from x to y, y to z, z to x and so on, right? So if I can go x to y, and then this becomes z to x, z to x, and then x goes to y and y goes to z and so on. So I mean you can, this is basically rotation about the x-axis, right? So if you just do that, so what you'll have is this thing you want. This is the rotation about the x-axis. So that quantity is minus Iy sine phi plus Iz cosine. Right? So, because in order to get this, you will need the second equation. Because y goes to z, so this x goes to y goes to z, and in the exponent, of course, again z goes to x. So to obtain this integrand, it is this second one which will be useful, and so that gives rise to this quantity. So then you calculate expectation value. You have to calculate expectation value of the y component and expectation value of the z component. So y component and x component expectation value is 0. And what you get finally is mu zt equals mu z0 cos gamma omega 1 or gamma h1. Right, so you start with magnetization along the z-axis. So when you do expectation value, so there is no y component to the magnetization. This goes away. Only the z part remains. Start with 0 and then there's a cosine. Okay, so the psi star psi will give you 1 over the spin space. So you are just left with this. Okay, so what does this tell you? Z component, whatever you start from, it will just keep going around like this. You know, it decrease, increase in the negative direction, and so on. So these, by the way, go by the name of Rabi oscillations. So if there is no, you're sort of also ignoring any relaxation process, and the RF is always on, then the Z component just cycles between positive value, negative value. Okay. This is the classical equivalent of you apply at resonance, there is a RF field. So RF field has the same frequency as the precession frequency, and so it exerts a torque. So what is the effect? As you see in the lab frame, it's going like this, the angle increases. Within the plane, it keeps increasing, other direction, back and forth, this will keep happening. This is the quantum mechanical equivalent, if you consider the expectation value.
So there is no magnetic moment component in x and y direction?
Right.
No component, only in z?
Yeah, I mean,
The rotated frame.
in the rotated frame.
Okay, in the rotated frame, yeah.
Okay.
Mhm.
So this is just to say you get back this mu z oscillates between some plus and negative value. Then another quick thing, because you had asked once before, so there's another way to describe this is you write this wave function psi prime in a spin basis. So you have a spin half minus half with some coefficients, and now here you put the time dependence in the coefficients. Okay, and then you do I bar del psi del t and so on. So here you will take time derivative of this a and b. These are just eigenstates, so nothing to do here. They're not changing. And then you do this, and then you know, on the right hand. So you want to multiply by, say, u star half from the left. And so some of it will give you 0 because they're orthogonal to minus half, the other will give you 1. And you can solve for A and B, basically. Okay. Where you will need to use what is, because you have in the Hamiltonian, so by the way, this is equal to h prime psi prime. The h prime has a ix. Okay. So you will, when you do this, multiplying from the left by u half and so on, you will, and here you have a ix, so you will get these kind of matrix elements, half ix minus half, for example, or the other way when you multiply, so plus minus half plus half. So this is actually as a value half.
I plus I.
Yeah, you have to do I plus I minus. The I minus doesn't do anything. The I plus will raise this, and then you have a prefactor there, if you remember. So you do all that, and the half is 1. Bracket half is 1. Only the prefactor square root of what is I plus 1 minus m plus 1. So that will give you half. So with all that, you can determine what the coefficients are. There's some interesting outcome of that anyway. So you get A of t as A0 cos omega 1 t by 2 plus I B0 sin omega 1 t by 2 and B of t. So you have a time dependent wave function where you are expressing this psi prime in terms of this complete set, half minus half, and the relevant coefficients have this time dependence. So the second one is I A0 sin omega 1 t by 2 plus B0 cos omega 1 t by 2. And of course this omega 1 is gamma
Minus I is
minus I. Minus I. You can sort of check minus I bar
sigma y is
b dt, then this will give plus h bar a0 omega 1 by 2 cos t plus minus h bar b0, so plus omega 1 by 2. And then this should be equal to gamma h bar h1 and then the matrix element which gives a half. So this is h bar omega 1 by 2 a. This is what it should be from just the Schroeder equation. Does it come out to be that? So h bar omega 1 by 2. It's okay, no? I mean, this is indeed A. So I think plus sign. You have to just solve for A of t and B of t by just putting back in the Schrödinger equation. Okay, so interesting outcome is that this is the variation of A and B, and we know that what this pi pulse, 2 pi pulse is. So interestingly, after 2 pi, because you have this divide by 2, the sign will give 0, but this will flip the positive to negative sign. So psi prime at t equal to t equal to 2 pi t 2 pi, okay, equals minus psi prime at t 0. So wave function itself comes back to its original after 4 pi. Yeah, so this is the spinor description. And apparently, there is experimental verification that indeed this happens. So the expectation value is okay. Okay, but the wave function itself changes sign in one 2 pi rotation and then comes back with another 2 pi. So after 4 pi, so 2 pi, the wave function is different, another 2 pi, then it's back. Expectation values are okay, the minus sign doesn't bother. So this is like a spinor description. So that's why this is.
Experimentally, the phase can be measured, or the phase difference.
So, he cites a couple of Abraham cites a couple of references, or maybe Schlichter, that the impact of this, I don't remember immediately as to how they verify. I'm also measuring the phase of the wave function in some way. But, so we should look at in this reference what they actually measured. But so this is an interesting outcome. Okay. So my intention was just sort of recap where we are. First we did was basically just classical treatment of spins, right? And then this dm by dt gamma m cross h, so like spinning top at gyroscope, etc. And then what amounts to resonance, and then what is the dynamics of this magnetic moment, and all that we could work out classically, going to rotating frames. And because only reason going to rotating frame is that the picture is easy there. You can picture what's happening because you eliminate the effect of the DC field and so on. But then we could also do a quantum mechanical treatment, and of course it gives the same. If you look at the expectation values, you get back the same equation. So again, this picture of precession, so magnetization going from plus to minus to plus to minus and so on. So again, you get quantum mechanically. Next, so this done. Next, what we look at is this relaxation processes. So now if you switch off the RF field, or let's say in between, after a pulse, phenomenologically at least, you divide it into a spin relaxation and a spin lattice relaxation. So there are these very ingenious block equations, whether ESR or NMR and all these resonance phenomena. So they introduce these parameters, T2 and T1. So what should be the relaxation law, and how do we apply in practice? And an interesting outcome which I already mentioned, not to do with the block equations, but the fact that you get this dephasing, but you can refocus this idea of spin echoes. So this spin echoes also you can in a quantum mechanical treatment, because it's just some rotation of wave functions, okay, rotation of magnetic moment. So one can obtain that. Maybe I'll spend later some few minutes on that. So basically what you are doing, remember you have a 0, then an RF pulse until T1, then at T2, a duration, let's say tau, there is nothing, only, so the H0 field is always there. In this pulses, you have the H1 field also at resonance, nearly resonance, and then one gives until T3, again RF pulse. So you basically have to look at the evolution of the wave function. So initially, suppose this were a pi by 2 and pi. So you apply these operators, and so you'll have Iz going from this direction to this direction. Then there's a time evolution because there's only a H0. So e to the I by h bar, what is the Hamiltonian time? That's the evolution of the wave function. Then again you have a pi pulse, so again something happens, and then again nothing. Okay. So what will be the time dependence of the magnetic moment in this region? So you'll find that you'll get basically a reproduction of what is over here. Quantum mechanically also. So little bit of effort, but it's just algebra involving this spin operators. Okay. So we'll do this, and then I mean, this is sort of in isolation, no, magnetic resonance phenomenon. But you are interested in looking at it in solids to probe something more intrinsic. So one is, what is this? You know, just nuclear magnetic resonance is okay, interesting concept, useful in many places, but our interest is in looking at solids. So there's this hyperfine interaction, electron-nucleus interaction. So there is a, so initially you just forget the RF field, you just have a Hamiltonian minus mu dot H, right? But you have an additional term because of the electron-nucleus interaction. Okay. So one will show that this basically amounts to having an additional field at the nuclear site. So whatever is the resonance frequency, if there were no electron-nucleus interaction, gets changed because of the electron-nucleus interaction. And the immediate impact is that the electron is basically having some magnetic property. So you have a magnetic susceptibility from the electron system, and that is basically causing some additional field at the nuclear side. So any shift of the resonance is because of the electron susceptibility. And so with some little bit of work, you can show that through a hyperfine coupling interaction, you can translate the susceptibility, the uniform susceptibility, Q equal to 0, omega equal to 0, to something called a night shift. Okay. So a measurement of the night shift in NMR allows you to indirectly probe the static susceptibility of your solid.
So this is local field. There are two types of field inside, local, internal, external. This here.
Yeah, this is internal. I mean, this contains external. So you have superconducting magnet, electromagnet, whatever. So you're placing the sample in there. The other one is always there. It's because of the electron-nucleus interaction.
So this is same as local field. Internal and local are same.
It depends on the context. I mean, this is the internal field from. I don't know what you mean by local or internal. The same.
Write one equation: H external equal to H local plus H internal.
We'll have to see what the context is there.
Internal, just sample.
It's not within your control. It's from inside. So this is one point. Yeah.
So this is the DC susceptibility?
Yes. So this is also, you know, chi is chi prime plus chi double prime. This is the chi prime, and at Q there's a wave vector dependence. So what we measure is this, the uniform susceptibility, static susceptibility. In fact, we'll see what the NMR signal measures. So this is one parameter. Then once we do a block equations, we realize that there is going to be relaxation, and that is parameterized in this T1 spin lattice relaxation. So, for example, one outcome is that for metals, so one can also calculate from first principles what this 1 over T1 is. You know this, there is a hyperfine interaction, no, A. So that is what is leading to decrease of energy of the nuclear spin system and corresponding increase with the electron system, right? So what is the transition probability, and therefore this integral, no, this can be written. So this can be calculated, and what one finally gets is that for metals, this k square T1T, okay, this measures the static susceptibility, this is the relaxation time, and T is the temperature. K square T1T is contains just fundamental constants. So I forget exact expression, but something like this, okay, I'm wrong by something. So gamma E is the electron gyromagnetic ratio, gamma N is the whatever nucleus is looking at nuclear gyromagnetic ratio, so again containing only fundamental constants, right, universal thing, squared, and is a prefactor h bar over 4 pi Boltzmann constant. So if a simple Fermi liquid, you know, k square T1T should have this value. It's like you can calculate the susceptibility for a free electron gas, right? If there's no enhancement for any reason, then you know the answer. Do you?
So chi dash Q0 omega 0 is only at paramagnetic region.
We are talking about a metal.
No, above one which you expression you have. This chi prime Q0 omega 0 is only at paramagnetic region.
No, K is measuring this.
I think one can detect the magnetic transition where this.
Magnetic transition one can detect, but one is always, by measuring a shift, one is directly measuring chi prime. The region is material. No? If there are, if it's a ferromagnet or something, then there is a, I don't know, you call it internal field, local field, there is a massive field because of the ordering. Then things will be different. Okay, but in that sense, paramagnetic region. But yeah, you are measuring this chi prime. For a metal, you can calculate the magnetic susceptibility. First principles. Do you recall what it is? Just contains fundamental constant, और कुछ नहीं है ना? Maybe off by a factor of 2 or something, depending on how you define this, but that's it. That's the free electron gas susceptibility. Right? The DOS at the Fermi level. Remember, it's only electrons at the Fermi level which contribute, because thermal energy is small compared to Fermi energy, you know, the usual argument. And so that's it. So the Curie variation is for localized moments, C over T, temperature dependent, but for, so this is Pauli paramagnet. So a loose qualitative argument is that, yeah, I mean, you still have local moments of electrons, but they're mobile. Okay, so you have a Cu by T, but what? But this is not, this is temperature independent, right? Density of state is temperature independent, UV square is temperature independent. But I'm saying usual stat mech you do, localized moments, non-interacting, in high temperature, low field, the susceptibility you get is Curie law. So why is that not applicable here? You have done this problem.
Yes.
You work out stat mech of isolated localized moments of spin J or whatever you get, Brillouin function, etc. You take it in the low field, high temperature limit, you get this for the susceptibility, temperature dependent, Curie law.
Yes.
I'm saying for a metal, it's actually this. I mean, it's temperature independent. In practice, you measure, you find it's temperature independent. So what went wrong? I calculated Curie, but in a metal, it doesn't seem to work.
Free electron.
Huh?
Free electron.
So, what's the issue here?
Transition temperature versus the
No transition of any sort. So, non-interacting localized moments, it gives Curie. These are not localized, but what else? You know, these are again non-interacting, same electrons. Itinerant, of course. What's the key here? You know it.
The state is changing with different something. Just remember this.
You have to explicitly take into account the fact that these are fermions, Fermi statistics. So, all electrons do not contribute. There's a basic problem, no? You have a Fermi function which goes like this. So, at finite temperature, okay, something like this, but still, this is much smaller compared to this.
Yes.
You know, this is like 10 power 4 Kelvin.
And this is
You know, this is like 10 power 1, 10 power 2 Kelvin.
Huh.
25 milli eV is the room temperature value or less, and this is like eV, several eV. As a result, it's only some fraction T by TF which contributes to this. Anything from a metal, all the electrons over here actually don't contribute at all, because you cannot excite these. No, their levels, there's no availability. They're all filled. You disturb only around the Fermi surface a little bit. So as a result, qualitatively you can say C by T is okay, but only some small fraction will contribute. How much? About T by TF, that's TF is the Fermi temperature. So of course the T cancels and you get, in fact the actual value you get is also not very far from this expression. If you put down what is the Curie constant and compare with this, it's not too far. Okay? Same argument for heat capacity. Classical answer for heat capacity is what? 3R.
Yeah.
So, metal, what should be the case? So, how do you calculate heat capacity? Again, you do a StatMech, calculate the energy, internal energy, take derivative with temperature, that's what it is. If you take 3R, there's no temperature dependence. I mean, sorry, other way, you get, I said wrongly. So, equipartition theorem says half kT per harmonic term in the Hamilton, really. Per degree of freedom. So, if you take just electrons, forget the lattice, then 3-dimensional, so 3/2 kT. So, that time temperature derivative, so 3R. 3/2. I mean, the lattice will be another 3/2, so that's why you get the 3R. Sorry, just to clarify, you will get some p square term, and if you have lattice, you will get a q square term. Okay, and so each dimension will get half kT plus half kT. Okay, so that's how you work out, and then that's the energy. Temperature derivative is the heat capacity, so you get whatever it is. What happens is, again, for electrons, because of the Fermi function and the relative values of your usual temperature and Fermi energy, it's only these electrons you are able to excite, so to get the heat capacity. So, and you have to apply, so you have to work out not with classical equipartition, you have to work out with applying Fermi statistics and work out the equipartition. So, turns out, I mean, this half kT per degree of freedom is wrong, right? It doesn't give you the right answer. It's okay in the classical limit. High temperature limit is okay, but it misses everything. But for metals, 300 K is low temperature. Okay, because Fermi energy is 10,000 K. Okay, so again, same thing. you can calculate the heat capacity and do a T over TF. Only that fraction contributes for the energy, for calculating the temperature derivative, and then you get the linear heat capacity, gamma T. Okay.
CV times T.
So for a metal you get low temperature, you get a gamma T, and again low temperature compared to the Debye temperature, then you get the actually a Debye function, but if you are low compared to the Debye temperature, then that gives a beta TQ. Okay. So the 3R and all is only high temperature. Okay, so you really explicitly need to take into account the statistics and actual form, etc. So main key point is that it's only electrons around the Fermi level which contribute to all these properties. So same goes for conductivity also actually, but there what happens is that you have a surface integral and then you convert it to a volume integral, so that way you can, then everything comes in. But it's really only some surface integral involving just electrons at the Fermi level which contribute. Okay. So anyway, so where we were somewhere else. So because from first principles you can calculate the Pauli paramagnetic susceptibility, which is temperature independent, and then you can see what the effect is on K through a hyperfine coupling, and likewise you can calculate the 1 over T1. Okay, that also contains the hyperfine coupling squared actually, right? So because transition, square of the matrix element, we have a Fermi golden rule for 1 over T1, so therefore you get a square. So if you do a K square, again you will get a square. So that part cancels. Okay, so this one just contains fundamental constant, no hyperfine coupling. Okay, and so you can calculate a number. Okay, so anyway, so this is called some S, and so in the real metal that when you measure, you want to check, so this K square T1 T by S, when S is this right hand side, this is called the Coringa ratio. Ideally, so free electron situation, it should be 1. You measure in your system, see if it is enhanced or not. So if you have a heavy fermion or something, then it should be heavily enhanced. So this is an important parameter. So this is an outcome of this, just calculating the shape thing in terms of the hyperfine coupling. So this will do, and then again in real materials, what is the shape of the spectrum that you get? In reality, you will have anisotropy because this can be anisotropic, this A can be anisotropic, so that has an effect on the line shape. We consider only spin half nucleus, so Hamiltonian is only the Zeeman term. You have a non-spin half, you have a quadrupolar term in the Hamiltonian. Electric quadrupole moment, and if there is in a crystal, so they have a neighboring electric field gradient, and so electric quadrupole moment couples with the field gradient. Another term in the Hamiltonian that changes things as far as the line shape goes, also as far as the T1 goes. So some of those things also we can see. So we'll figure out next class, but next is then these block equations. Yeah, so these block equations and how the spin echo arises. Okay, I just quickly mention how you write the operators and then you basically recover this if you don't include any relaxation. In reality, there is a T2 and a T1 relaxation, so of course this will be smaller than this one. Yeah, so we'll stop here. Today you have a pen drive or not?
No, sir.
So,
We'll take
class
so hopefully it will remain.